Welcome back to the deep dive. Today we are strapping on our forensic safety gear and going deep, really deep into a single, highly specific incident.
That's right.
It's a moment of, I think, profound technological clarity. It was caught on camera, and it speaks volumes about the true current state of cutting-edge humanoid robotics.
It really does. And we are not interested in the glossy corporate roadmap today or, the future-gazing white paper. Our mission is surgical. We are analyzing one piece of highly critical user footage, one split-second event, to figure out two core things for you.
Okay, what are they?
First, what exactly happened when a high-profile robot failed so publicly? And second, what does that specific failure reveal about the massive conflict between, the corporate claims of autonomy and the operational reality of human control?
And our source material is incredibly concise. It's basically a report detailing some user footage that was captured on Reddit, and it zeroes in on the exact moment a Tesla Optimus robot revealed a pretty significant operational secret.
A secret it was never meant to show.
Exactly. We're going to unpack this specific, very human-like VR tell and really try to understand its deep systemic implications.
And the initial framing here is, I think, critical. This deep dive isn't just about general robotics progress, it's a forensic examination. We're attempting to establish definitively where the line currently sits between genuine, independent AI handling complex tasks and the absolute necessity of real-time human teleoperation in these dynamic public-facing environments.
And that gets us to the big questions, right?
It does. This is what we answer. Can a person actually control a robot using VR? And, how difficult is it really to create a moving robot that looks and acts like a human?
Okay, let's unpack this. We have to start with the scene itself. We need to visualize the stakes of this moment.
Right.
The stage was set at a high-profile Tesla event in Miami. When you hear the name Tesla, you immediately think innovation, radical future thinking, huge public hype. So what does presenting a functional humanoid robot at a major high-stakes public gathering like that, what does that imply about the company's confidence level in the platform? They weren't just showing it off in a controlled lab.
No. That decision implies a degree of perceived stability and readiness that is far, far beyond the typical R&D lab prototype. A major public event, especially one orchestrated by Tesla, doesn't just display technology. It functions as a definitive statement of imminent market reality.
Right.
By placing Optimus in that context, they are effectively telling investors, telling the public, look, this system is robust enough for prime time, it's nearing commercial viability.
And because of that, the stakes are just astronomically high.
Precisely. The company has poured resources into ensuring the demonstration is flawless, knowing that any slip-up will be captured immediately and become instant viral evidence against the entire program.
Someone's always filming.
Always. They're trying desperately to shift the narrative from, say, a speculative R&D project to a polished, marketable product that can soon replace human labor. The environment alone creates maximum pressure for performance.
And what was Optimus's specific job? It wasn't just walking across the stage or waving to the crowd. It was actively engaged in a service role, distributing drinks. That seems like a carefully selected but also surprisingly complex task.
No, it's the perfect demonstration task, precisely because it's so deceptively difficult. On the surface, the action is mundane, right? Navigate, pick up an object, walk, and gently hand it over.
Sounds simple enough.
But that task highlights two absolutely essential functions they need the public to focus on, and two that are incredibly difficult for a machine.
And what are those two functions?
So first, you've got sophisticated mobility in a complex, unpredictable environment. The robot has to walk amongst people, navigate potential obstacles like, uneven floors or suddenly moved furniture. And all this requires continuous, low-level environmental sensing.
And the second?
Sophisticated object interaction. This means careful gripping, sensing the weight of the liquid which shifts as the robot moves, and adjusting its center of gravity constantly to manage the liquid sloshing around.
Wow. Okay, so that sets a massive expectation of sophisticated, reliable function. The audience isn't just watching a machine moving, they're watching a machine operating smoothly in a service role, simulating human efficiency.
Exactly. If the robot was just doing a repetitive motion on an assembly line, that would prove nothing. But serving a drink suggests decision-making, path correction, and most importantly, dynamic stability in a generalized human setting.
That combination, dynamic stability plus generalized interaction, That sounds like the real computational hurdle.
It is. Dynamic stability is especially challenging for bipedal humanoids.
Mm.
I mean, think of a human. We rely on thousands of years of evolution to maintain balance subconsciously. For a robot, every single movement, every shift of weight, every step, every minute adjustment while holding a tray requires constant microsecond calculations based on sensor input.
To keep from falling over.
To maintain the zero moment point, or ZMP, that process, which, humans take for granted, must be explicitly programmed or, as the evidence we are discussing suggests, actively managed in real time by something else.
Or someone else.
Precisely.
And the transparency element here is what makes this footage so valuable. The incident was captured by a user on Reddit, disseminated immediately. It wasn't hidden or edited.
This immediate public dissemination, it really emphasizes the modern reality of these high-profile tech demos. In the past, companies could control the narrative completely.
Right. They'd release their own polished video.
Exactly. But today, every audience member is a potential journalist. The presence of hundreds of phones means the audience acts as a massive, distributed quality assurance and forensic team. Every glitch, every slip-up becomes unvarnished public data instantly, which is why this specific piece of footage is so high value for us.
Okay, so let's detail the sequence of failure that the footage captured. Our source breaks it down into 3 distinct, rapid-fire parts that tell the story of the collapse. The robot is doing its thing, distributing drinks. Then, first, it performed a strange movement with its hands.
And that specific movement, that initial anomaly, that is the single most important clue in this entire story. It is the defining tell.
Yeah.
Without that gesture, we just have a robot that fell over, which is, a common failure mode.
But with that gesture.
With that gesture, we have proof of an operational mechanism.
So second, immediately after that strange hand movement, the robot disconnected. And third, it then fell.
What's fascinating here is the absolute causality.
Yeah.
The source links that strange movement directly to the subsequent immediate failure, the disconnection followed by the fall. This sequence is highly unnatural for a truly autonomous system.
How so?
Well, if the robot were truly autonomous, a simple error in hand placement or grip shouldn't cause a catastrophic immediate system shutdown leading to a gravitational failure.
Right. An autonomous robot should have some kind of local redundancy. It should have a system and internal protocol to catch itself, or at least transition instantly to a safe, static, maybe kneeling or braced posture to wait for instructions.
Exactly. The fact that it just fell suggests a sudden, complete, and total loss of its dynamic operational control core. It didn't wobble and then fail. It went from functional movement to inert collapse in fractions of a second.
Which brings us right to the core mystery we need to solve. What exactly was that strange movement?
This is where we have to focus exclusively on that characteristic gesture, because it is the linchpin. The source states this gesture was recognized instantly by people who saw the footage as a human removing or adjusting a VR headset from their head.
That instant recognition is the key.
It is. People who use VR for immersive control or for gaming, they recognize the movement not as a machine error, but as a human habit. The hands moving up, slightly pushing out, and then down. The motion of disengaging from an apparatus strapped to your face.
Okay, here's where it gets really interesting and where I have to challenge the premise a little bit.
Go for it.
Couldn't that gesture have just been some pre-programmed debug sequence that coincidentally looked like someone removing a headset? I mean, is this really definitive proof? A robot doesn't get sweat in its eyes or need to adjust its nose pads. Why would it mimic sweeping something away from its face?
That's a fair challenge, and it forces us to be forensic. While coincidence is, always possible, the failure sequence argues against it.
Okay.
If it were a pre-programmed debug sequence, the program itself would include the instructions for the next steps, either recover or shut down gracefully. It wouldn't include instructions for the robot to become instantly inert and crash. The robot wasn't performing an internal task. It was mirroring the external operator's involuntary or habitual action.
Aww.
This replication of a distinctly human, non-functional movement is the technological smoking gun for high-fidelity teleoperation.
So, if the machine was mimicking the operator, we are talking about direct high-fidelity mapping.
Yes. This strongly implies an immersive control system. When a human controls a complex dynamic machine like Optimus using VR or immersive telepresence, the system has to achieve one-to-one fidelity. It needs to map the operator's physical actions, hand movements, head tilts, core balance shifts, body posture, directly onto the robot's actuators with minimal latency.
So the robot is acting as a direct, high-definition proxy. If the operator makes an unconscious, habitual movement like stretching their neck, adjusting their posture, or reaching up to relieve the pressure of the headset.
The robot replicates it precisely. The instant recognition by the witnesses confirms the action was perfectly human, executed by the machine, which in turn confirms the control method and its level of fidelity.
This is a powerful, circumstantial, but pretty undeniable answer to our question. Can a person control a robot using VR?
The evidence suggests emphatically yes, and that the control is so immersive that it transfers even the operator's involuntary or personal comfort gestures.
Okay, let's delve a bit deeper into the technical implication of direct mapping. This requires a continuous real-time control link. This means the human operator wasn't just, say, initiating a macro function like walk to the table.
No, not at all.
They were actively driving the robot's moment-to-moment actions and, crucially, maintaining its dynamic stability. It wasn't running on a pre-programmed script, it was being piloted.
And this brings us to the hypothesized motive of the operator. The source suggested that an operator situated nearby decided to take a break, or, as the original source phrased it, and disconnected from controlling the robot. This sounds like an incredibly human, casual action, but the timing is catastrophic.
They just decided to quit the session, remove the gear, and the robot collapsed.
The act of disconnection, removing the heavy, cumbersome VR headset, was apparently the exact physical action that triggered the control signal to be lost or dropped. This indicates an immediate physical link between the operator's state engaged versus disengaged and the robot's operational state. And crucially, there was no graceful handover protocol, no buffer, no programmed fail-safe procedure, and definitely no internal autonomous system ready to immediately assume stability control.
Not even for the few seconds it would need to balance itself after the human pilot decided to quit.
Not for a millisecond.
The consequence is immediate and stark. The robot ceased showing signs of life, or away, immediately after the physical gesture, followed by the fall. That phrase, ceased showing signs of life, is chilling because it emphasizes the sudden cessation of all intelligent control.
And we connect this to the bigger picture. This entire sequence proves that this complex task-distributing drinks in a public environment was not primarily autonomously programmed or handled by an internal AI. It was wholly dependent on real-time, external human input. The robot's dynamic stability, which is the hardest physical task for any humanoid, simply vanished the moment the human pilot effectively logged off.
This brings us back to one of the core questions. How difficult is it to create a moving robot that looks like a human? I mean, why did the robot fall so immediately? Why was there zero transitional stability?
This is the massive technical challenge, and it's where the engineering budget goes. It speaks directly to the immense, often underestimated difficulty of true bipedal movement. For a static factory arm or a simple wheeled robot, if you lose control, it just stops. For a humanoid, you are battling gravity and high-order physics equations in real time, constantly.
Right. We as humans, we rely on these complex, deep-seated reflex loops, our highly sensitive vestibular system in our inner ear for balance, and continuous low-latency sensory input to maintain balance without even thinking about it.
Absolutely. And to achieve that level of dynamic stability autonomously in a dynamic environment, which includes people moving, slight bumps, floor changes, or just the weight shift from handing over a drink, is an incredibly demanding and currently unsolved computational problem for generalized AI.
You mentioned the zero moment point earlier.
Right. The software must be constantly calculating its ZMP, which is the single point on the ground where the total sum of all forces and torques results in no moment or rotation. If the robot's center of gravity moves outside its small support polygon, basically its feet, it falls.
So when the human operator is in the loop via VR, they are essentially providing that high-level, intuitive, low-latency balancing input. They are acting as the immediate nervous system, the reflex mechanism.
Exactly. Think of it like a complex vertical stack of children's blocks.
Yeah.
If you are standing next to it and you feel the central stabilizing hand remove itself, that's the human pilot, the stack collapses instantly because all the necessary micro-adjustments required to keep the center of gravity aligned with the base stop immediately.
There's no intermediate wobble.
None. The hardware is there, but the operational brains for dynamic stability were removed with the headset. The instant fall confirms the human was the stabilizing force, not the AI.
And crucially, what about the issue of latency? That has to be discussed here. Even the best teleoperation systems still have latency measured in milliseconds. Why didn't that latency cause constant instability during the successful part of the demo?
That's a great point. The latency is always there, but the skill of the human operator compensates for it. They are predicting the robot's movements and correcting them before the lag becomes catastrophic. They're always driving ahead of the curve.
But when they rip off the headset?
Exactly. When the operator rips off the headset, the control signal doesn't degrade slowly. It drops to zero instantly. That instantaneous loss of the predictive, low-latency human input is what caused the immediate fall. The robot's localized AI, if it existed for stability, had zero time to react.
It's a compelling, detailed piece of technical evidence. It confirms both what happened and the profound dependency on VR control for these delicate, dynamic tasks. But this technical reality now slams directly into the corporate narrative.
Right. And we have to pivot now from the technical failure to the corporate narrative failure. This incident provides a direct and frankly embarrassing contrast to the very public claims made by the company's leadership.
We know the CEO had asserted that the Tesla Optimus robots were performing various actions quite independently. Or, agoroa, that's a strong statement. It suggests full autonomy, or at least a very high degree of delegated autonomy.
The corporate narrative must focus on independence and autonomy because that is the industry's holy grail.
Why, though? Why is that so important?
Because autonomy equals scalability, reliability, massive performance potential, and ultimately massive profit without corresponding labor costs. Investors, engineers, the public, they're all sold on the dream of a truly independent, functional humanoid workforce.
And what's the financial opposite of autonomy?
Teleoperation.
Teleoperation, while it's a brilliant feat of engineering, implies dependency. It requires a human supervisor, often at a 1-to-1 or maybe 1-to-2 ratio. That means high operating costs, continuous human wages, and a severe limit on deployment scalability.
So if every Optimus needs a human VR operator nearby, you haven't really solved the labor problem.
You've just created a new, expensive human-machine interface job. The economic pressure to claim autonomy over teleoperation is immense because one promises infinite scalability and high margins, and the other promises operational overhead.
So we're talking about the critical difference between a proof-of-concept prototype showing a capability like it can walk by itself for a few steps, and a polished, demo-ready function that is reliable enough for a public display.
Exactly. The company wanted to demonstrate the latter, but the incident proved they were reliant on the former human direction to successfully navigate the complexities of that demonstration task.
And let's address that crucial question again. Was the VR control a backup, or was it the primary control mechanism for the demonstration task of distributing drinks? Well, the speed of the disconnection and the subsequent fall is our best evidence. As we discussed, if it were merely a backup system intended only for handling exceptions, we would expect to see a momentary lag, maybe a wobble, followed by a localized AI taking over for basic stability before the collapse.
But we saw none of that.
The immediate lights-out failure mode strongly indicates the human was the central processor for balance, movement, and environmental awareness during that specific moment.
That is the crucial distinction.
It is. Teleoperation is perfectly valid in robotics. It's often used to handle tasks that are too novel or complex for current AI, like a weirdly shaped glass or a surprise crowd movement. But the nature of this failure implies the VR operator was providing the core dynamic control necessary to execute the entire sequence. And that tells us a tremendous amount about the current functional limitations of the Optimus platform.
And that leads directly to the core conclusion drawn in the source material, which is that full autonomy, the kind that can truly replace human labor in unpredictable settings, is likely still far away.
Or Ji Zhenjin Wool, as the source says. And based on this forensic evidence, we understand why. Full autonomy in a humanoid requires generalized intelligence, the ability to perceive, plan, react to entirely novel, spontaneous situations, and maintain dynamic stability all at once without external human intervention.
And this incident shows that capability is currently lacking.
At least for the relatively simple but generalized task of gracefully navigating a party and handing over an object.
So what does this all mean for you, the listener, who wants to quickly grasp the state of play in humanoid robotics? It's a moment of immense clarity because it teaches you what to look for. It suggests that highly dynamic, public-facing robotic tasks, especially those requiring delicate balance and spontaneous interaction with humans, still require a human co-pilot, or in this case, a primary driver using high-fidelity telepresence.
And we can definitively answer one of the core questions this deep dive set out to address. Yes, sophisticated humanoid robots like Optimus are demonstrably controlled by people using VR or immersive telepresence, at least for the most complex demonstrations.
The removal gesture, that tiny piece of human behavior, confirms the method and confirms the dependency.
This wasn't theoretical. It was operational reality caught on camera and magnified by the system's failure mode.
The key takeaway here seems profoundly simple when you look at it that way. The failure wasn't a mechanical one, but a human one, magnified by technology. The robot didn't fail to grasp the cup because of a programming glitch.
No, it failed because the operator got uncomfortable or momentarily distracted and broke the link in a perfectly recognizable human way. And that tiny piece of human behavior, the impulse to remove a restricting device, translated into catastrophic physical failure for the machine.
It just highlights the profound, almost unsettling connection in a teleoperated system. The robot becomes a literal, high-fidelity extension of the operator's physical and even habitual self.
The boundary between the person and the machine temporarily vanishes, only to reappear with a thud on the floor.
We've reached the synthesis point of this deep dive, so let's bring this analysis back to the critical findings we extracted from that single piece of user footage. A Tesla robot failed publicly in Miami because a nearby operator likely made a recognizable, common human error.
Disconnecting via a headset removal gesture. It's high-value data because it cuts through all the marketing hype. This single moment provides immediate, unvarnished insight into the current functional limitations of cutting-edge humanoid robotics.
It shows where the line currently sits.
Exactly. The most difficult dynamic tasks still require robust, real-time human intervention via VR teleoperation, despite the corporate claims of independence.
The value of this slip-up for you is that you now know how to differentiate between marketed hope and technical reality. If a robot is performing a complex, dynamic task in an unpredictable setting, especially one involving navigating people,
there is a very high probability that a human is the co-pilot, if not the main driver. And if that human makes a mistake, the robot, like Optimus, will simply fall over, confirming the state of its dynamic stability protocols.
it demonstrates that the current technological challenge for these robotics programs is less about perfecting the individual components, the arm movements or the sensors, and more about achieving that seamless, instantaneous transition.
A transition between fully human control, semi-autonomous assistance, and full autonomy, especially when dynamic stability is paramount. The engineering bottleneck is the generalized brain, not the muscle.
We have spent this entire discussion focusing on the operator disconnecting and the robot failing publicly. But let's leave you with a final provocative thought to mull over as we close this specific deep dive.
Okay.
The discussion has centered on human control disconnecting and the subsequent collapse. Consider the future implication. If the economic and public pressure to claim autonomy remains this intense, how much of a robot's operational code is dedicated not to perfecting movement, but to seamlessly hiding the moments of human takeover or handover?
That's a fascinating question. If autonomy is the goal, then the greatest engineering challenge might be creating a system that can smoothly transition from human control back to autonomy, or vice versa, without the robot making that strange human gesture, without wobbling, and certainly without collapsing dramatically.
The demonstration itself then becomes a layer of sophisticated performance art designed to mask dependency.
The ability to flawlessly mask human dependency will likely become the new metric of success in public robotic demonstrations. Hiding the human pilot's engagement and disengagement will be the ultimate technical hurdle for dynamic humanoid robotics.
Thank you for joining us on this very specific, very forensic deep dive into the true state of dynamic stability and human control. We hope this insight helps you better judge the next round of technological demonstrations you see. We'll catch you next time.